right? Like you can go on package, and there is an parsec, and there is an parsec text, and they are basically copy-paste jobs of each other. And that's terrible, because we're Haskell, we're all about, writing at a high level of abstraction. We don't want to, deal with this. And the problem's worse, because, if you look at, any language library which wants to use, say, the parser, and they also want to be parametric over the string type, well, now you have to do multiple implementations. It's worse because, a lot of the times they don't bother, so you're using byte strings, and you needed, a DDD parser, and, well, the library's not there because the person who wrote it, was only working with text, even though the code was sort of modular in a way that it could have been used in the other situation. And to make things even worse, let's say that you're a guy and you're working on a new awesome string representation called in a library called Foundation. Well, now you have to rewrite the entire Haskell ecosystem to use your new string representation. So that's the situation we are in today in the Haskell ecosystem. So what can we do? But before I tell you what we can do, let me give you another example. So the Unix package is one that you should be familiar with. It comes with GHC by default. And if you look at the module list, you'll notice something very strange. Each module shows up twice, once sort of normal and once as byte string. And the reason is historically the Unix package provided interfaces for string. But there were many cases where byte string was more appropriate, and so they gave byte string versions of everything. And once again, how did they implement these two modules? They did a copy-paste job, simply rewriting a few function calls to use the analogous variant for the different type. And the problem with copy-paste is sometimes you get it wrong. So when I was working on backpackifying Unix, I noticed this bug. So in the string implementation of putenv, there's this very oblique comment saying that we have to not free the C string we allocate according to the file path, because when you putenv, you're transferring ownership of it. And the byte string version didn't do it correctly. So this would have seg faulted if you were using it. So I filed an issue on that. But copy pasting is bad. I don't think I need to emphasize how bad copy pasting is. So what can we do? So what is the solution? And I wouldn't be here if I didn't have a solution for you. And so the answer is Backpack. So what is Backpack? So Backpack is a way of writing a package where instead of specifying exactly what your dependencies are, you instead leave it indefinite. You say, let me have this component, but let me carve out a little piece of it which I'm not going to specify a particular implementation. Instead, what I'm going to do is I'm going to write a signature specifying the types that I need this module to provide, the operations I need for it, and then for each of the sort of string types I want to support, I'll simply have a separate package for each which exports a module that implements this interface. And so the idea then is that if we don't have a particular implementation, well, because I wrote an explicit signature, an explicit type, I can still type check this package and make sure it makes sense. And I can also, hook up an implementation, say byte string, to my package in order to get a version of, say, parsec, which works on byte strings. The way I do this in my Cabal file is I simply say I want to use parsec indef, and I want to use byte string. And sort of the thing about Backpack is it automatically then decides, oh, the missing implementation of parsec should be implemented using byte string because I needed something named string, and byte string provided something called string. By the way, feel free to shout out questions if you're confused. And so if I want to use a different package, then I just change my dependency from byte string to text, and now I have wired up my parsec package with a text implementation. And so the only thing, if you want to make a new implementation of the string package, all you need to do is make sure that your module matches the signature provided by parsec. You don't have to do some sort of complicated process whereby you build for every possible configuration with these packages because you're not sure exactly what is needed, what is not. You just look at the signature, and the signature tells you exactly what you need. So signatures also reduce coupling, because when you have an actual implementation, the temptation is to use lots of private methods that you really shouldn't use. Come in. So the other thing about Backpack is that you do not have to specify how the string is going to be implemented to still write more packages. So in this example, remember we had the DDD package which wanted to use autoparsec. So we can in turn define a DDT package which is parametric over the string representation. And the way we do this is simply by depending on autoparsec indef, and then that's it. And the whole, the string, missing implementation simply gets propagated out to DDD. So in this way, we can build an entire ecosystem which is parametric over a string package. And only at the very end does a user have to specify what implementation they want to use.
What if DTD and autoparsec have different requirements on what they need out of the string?
Aha! So as long as those requirements are compatible, let's say autoparsec needs some set of methods and DDD needs some possibly overlapping set of methods with the same signatures, what you would like is for the string to just be the combination of those two signatures. And that is in fact what happens with Backpack. So okay, big slide with lots of text on it, but let's sort of go slowly. So what do we want to do? We want a way to parameterize our Haskell code, not at the function level, not at the type class level, but sort of at the very biggest level we build our software, namely the package level. Because why do we care about modularity? We care about modularity when we're building large systems. So it's not smart. It's like a giant missed opportunity if we don't have the ability to take advantage of modularity when we're building, when we're using our tools for building large software. We can also, there's also other really good reasons for doing this. One is that Backpack, we sort of, one obvious thing to do if you know ML is you might say, oh, but Haskell should just get ML functors. There should be, new syntax. You should get, a way of specifying, like a module inside a module, and have it be parameterized, and then that would be nice, right? And the problem with that, and so the problem with traditional style module systems is they're basically another language inside the language. So think about how complicated Haskell is today with all its features. If we added ML modules to Haskell, that would be yet another surface language feature that you would have to understand and deal with to write code effectively. Whereas if we bring the parameterization to the package system, we can keep the surface language sort of simpler. Like you basically, when you write Backpack code, the goal is for it to basically look like normal Haskell code. You're just importing signatures rather than regular modules. Another reason why Backpack operates at the package level is so that we can adopt Backpack without breaking backwards compatibility. So if you look at the example here, where we have autoparsec, which brings together autoparsec, indef, and text. So we can make this an actual package that we upload on Hackage, and now all those people who are depending on autoparsec can use this package, and they'll see a version of autoparsec that works on text and is it's exactly the same as it was before. And if you want to be able to parameterize, if you want to write your software so that it is parametric over string, then you use the new package autoparsec indef. But you don't have to break backwards compatibility with all the software ever, which is what you would have to do if you were going to go ahead and functorize your code. And so also I'm an academic, and we kind of want to come up with new ideas. Putting ML modules in Haskell is not a new idea, but like mixin packages, that's kind of interesting. That's kind of cool. So where can we go with it? So I said mixins, and so I want to say a little more about that, because this is something that kind of is also interesting about Backpack. So some of you may be familiar with mixins from other languages like Ruby, or I guess React has mixins. The idea behind mixins is you have these components, and you sort of include them into your class traditionally, and then somehow they can talk to each other because they provide some functions and they need some functions, and if you wire everything up, things work okay. So the idea, so we also adopted a mixin-based design, but we sort of sidestepped some of the problems associated with mixins traditionally because our mixins are explicitly typed. So you know exactly what the requirements and the provisions of a package, the package is the mixin, are. And now what you basically get is you get the ability to sort of pass around the parameters that you're going to fill in packages with without having to manually write, oh, let A equal, A from this package, let B equal B from this package, let C equal C from that package. Instead, the mixin paradigm simply says that when you depend on some packages with holes, if you have another package in scope which exposes the same module, you can just, I don't have an example on this slide, but if you have a package which has a hole named P and another package which provides a module named P, then automatically you link them together. Yes?
Is it also possible to explicitly fill the holes with specific packages in case you have like multiple potential?
Yes. So I don't have any examples on my slides of this, but what you can do is you can take a requirement and rename its hole to a different name so that it doesn't conflict with, say, a different package which has that same hole. And we could also add a syntax for explicitly instantiating packages. We didn't, just to keep the syntax simple for now, but maybe if people ask for it a lot, we can put something like that in. So, but the default mode of operation is, sort of to take advantage of naming to, make it so that you don't have to write lots of boilerplate, lots of explicit functor applications if, you've done that in ML, and just get things implicitly because you name things that way. So like convention rather than explicit configuration. And this sort of meshes nicely with sort of a lot of the ways that people, write Haskell today. Like, when you have byte string and you have the lazy version and the strict version, oftentimes you would like to have just, had some byte string that you import, and you import qualified as BS, and that's sort of like the shared module namespace that you either put in lazy or you put in strict depending on what your module needs. So mixins sort of help make code more implicit and reduce boilerplate when you're writing functor applications. Okay, so that was like a super whirlwind tour of how Backpack works. The high points were that we have packages, you can put holes in packages so that you don't have to provide all implementations for modules up front. You can just have a signature instead, and then there's a way to specify how you want those signatures to be filled. So
I have a question.
Yes.
Is there any kind of like orphan signature problem that comes up where?
Great question. So the other thing about mixins, which I forgot to say, but thank you for reminding me to say it, is that, so say I have two packages which have a requirement which is named the same, and I include both of them in the same package. What happens is then those requirements get merged together. So let's say H referred to some type T and it had needed some operations, and this H referred to type T and also needed some other operations. Then when I put these two packages together, I should get a single signature with a single type T and the union of all the operations on both of them. And so unlike type classes where you define a type class up front and then only things that explicitly say they implement that type class actually implement the type class, signatures are an egalitarian mechanism where sort of the matching is implicit. You don't have to explicitly say that you implement a signature. If you provide all the types and all the functions that the signature requires, then you already implement the signature.
So it looks like you've implemented it than you have as far as
Then
the
you have.
systems.
It's like duck typing
Yeah.
in the Go sense. Were there other questions? That was a great question. Thank you. I almost forgot to mention that. Okay, so let me tell you a little bit about how Backpack works. So I tried to make the argument that, one, we wanted to make an extension to the package language to let you have parameterized packages. And so this leads us to sort of the primary challenge for implementing Backpack, which is that we needed to somehow design this extension in a way that sort of works with both the package manager and the compiler, because there's parts that we need to understand in both. And this is kind of difficult because traditionally we think of the compiler and the package manager as having a very strong abstraction barrier between them. The compiler takes single files, compiles them, and that's all it knows. And the package manager, looks at the global picture and actually, figures out, here are all the source code I'm going to build. Here's the order I'm going to build it. Here's where I'm going to put all the installed products. So Backpack. So the compiler does all the dirty work, and the package manager knows nothing about the source code traditionally. So Backpack breaks the abstraction barrier because we need the package manager to tell us, what are the holes on our packages, how are they linked up together, even to have a plan of what things we're going to build. But the compiler needs to know about signatures. It needs to know about how everything was wired up, because that's an essential question for type equality. And when I want to type check against a signature and when I want to merge signatures together, that's something that the compiler needs to be able to handle, because that requires knowledge of source code. So if you read the Popple paper, basically it punts on this issue. It's like, package manager, compiler, they're all the same piece of software, whatever. We're just going to have some sort of monolithic thing that knows how to handle everything. But sort of, let's not do that. So the key idea for Backpack, and I'm going to preempt a slide that I have later in this deck, is that if we sort of take as a given that the package manager knows nothing about the source code of Haskell packages, then we can cut out a division, designing a new intermediate language that sort of compiles away the mixin linking and all that stuff and gives you something very explicit that then the compiler can deal with. So let me just first tell you about how packages are compiled in Haskell today. So the current abstraction, right, is you have some source package, you feed it to the package manager, it does dependency resolution, it figures out all the source code you're going to build, and then you end up with some resolve package, which you then pass on to the compiler to compile. So the compiler just compiles a package at a time, giving you some interface files and some object files. Let's dig in deeper. So if I run cabal install autoparsec, or if you guys use stack, then you can say stack build. Then what I first do is in the bystring, which is one of my dependencies, I run the install script for it, and similarly for autoparsec, I need to run the build script for it. And what do those do? Well, they make invocations of GHC, which actually build the modules in question. And then the package manager actually takes these compiled products and puts them somewhere well known. Something to note is that when I build bystring, I give it this thing called a package ID, which specifies, sort of what the unique identifier of this package is going to be, because autoparsec could be compiled against, different versions of bystring. So, we need to be able to distinguish between those cases. It also specifies what the dependencies of the package are. And, like internally, we call GHC on each module one at a time to actually build in question. So this is sort of like the current way the package manager and the compiler interact. The package manager, gets invoked for every package, and then the compiler takes over and actually builds the things in question. So what we need is we need a new language for this command line interface, which can actually support the functionality we want from Backpack. And so what are we going to do? Well, we can add a pile of new flags to let us, specify signatures and things that we want. But instead, what we're going to do is we're going to design a language to represent these command line flags, because we're programming languages people, and when we have a hard problem to solve, we write a new language to deal with it. So what we have is sort of in the pre-backpack world, we can describe a component that GHC is going to build as something that has a dependency and then has some number of modules. And to the package manager, these modules are opaque. They know nothing about it, but they know that they want to build data out of parsec, and they want to build data out of parsec types. And the compiler actually goes and looks at these to compile it, and looks at the dependencies to figure out sort of what modules should be in scope when you build them. So diagrammatically, we can sort of view this as this byte string, providing some stuff to autoparsec, which then provides two modules. So if the package manager is source code independent, then if we want to have parameterized modules, one of the things we need to say is that signatures are something that we associate with packages, not with modules. Maybe this is obvious to you, but it wasn't obvious to, say, those of us who were reading Backpack in Popl 14, which actually had something that depended on what you transitively imported to say what you depended on. So the model we're going to have then is that a component consists of some number of modules and some number of signatures. And those signatures are going to be the holes that the package are parameterized over. So diagrammatically, I've got this component box, and it's got this input port string representing the module that I need to fill in. So this idea of mixin linking, where when a signature and a signature have the same name, we combine them together, or when we have a signature and a module with the same name, the module fills in the signature. What we're going to do is we're going to decouple this algorithm into two parts, one which is language agnostic and the package manager carries out, and another which is language specific, which GHC carries out. So the language agnostic part is actually very easy to explain. You take all the dependencies in your packages. So in this case, we have autoparsec, which depends on byte string, which depends on autoparsec in def. We sort of draw the component boxes with the labels. So this label is string, this label is string, and then we just wire up all the ones that have the same name. And that gives us our sort of wiring diagram, our series of functor applications, which specify how things are implemented. So once we do that, we can compile it down into a new variant of the component language, where we say, okay, we have dependency on byte string, that's normal, nothing's changed. And our dependency on autoparsec in def is a string says, okay, I want this package, but I want the whole named string to be filled with byte string, which is another module that came from a different package. So now, sort of, this is a very implicit way to write packages, and this is an explicit way to write the dependencies on packages. The language-specific part of mixin linking looks at the actual signatures in question. So, for example, we have autoparsec and we have DDT. They have different methods that they need, and the compiler runs to generate a new signature, which is the merged version of these two signatures. And currently, the merging process is very dumb. All we do is make sure the types exactly match, and if they don't exactly match, then we say, oh, we can't merge these.
Are we going to have a smarter process come A4?
Not for merging, I think, but for matching, so matching also requires exact type match, and you can imagine relaxing that. So you can implement string to string using a function that's A to A, but that's not something we know. Yes.
Yeah, does this incur any performance cost due to the inability to specialize functions?
Great question. So one of the explicit goals for Backpack was for there to be no performance cost when you use Backpack. So the idea is that whenever you fully instantiate a package, we recompile it from scratch for that particular instantiation. And this is another reason why you want to put it in the package manager, because if you don't, then you have to deal with this problem reminiscent of C++ templates, where you don't know when to generate code. If you generate it at useSite, you regenerate the code multiple times and have to deduplicate it when you link. But the package manager knows when something is used multiple times and can compile it only once. So that's a really useful thing. So the third thing is, there's a bunch of extra operations the compiler needs to support, but I'm kind of running low on time, so I'm going to skip them. But we need to check if the dependency linkages are well typed, because I said the package manager knows nothing about source code, so it has no idea if filling in a module with a signature with some module actually was okay. It needs to know how to merge signatures, and it needs to know how to instantiate components and refine the types based on the module you put in. So there's some stuff to do that, but the overall new abstraction, right, is that instead of just having dependencies in modules, we have dependencies on these parameterized packages. So they're not just plain old references to Q or P, but they also say how they are instantiated, and we can also have signatures associated with our package, which also specify sort of things that we don't know the particular implementation of and are being left parametric, as is indicated here. So this translates into some obvious looking new command line flags. Really not that many new extra things. So here's the new pipeline, right? We resolve dependencies, we mix and link, and then we type check and compile. Okay, so I did a bunch of case studies. So the example from the beginning of the talk, Unix, this is like the full signature you need for the example I gave. So these are all the operations that are shared between string and byte strings. You just write the signature, it looks like what you would expect, and then you have an implementation for string and an implementation for byte string, and then when you write your code, you just import the signature instead of the actual implementation, and it just works. Another example that I had was from Hackage. So there's this package called tag string conduit, and what they have is they have a version for text and they have a version for byte string, and this is the sort of parametric version of the library. Instead of having one signature, it has three signatures. It has a signature for strings, it has a signature for building strings efficiently, and a signature for parsing them as well. And the string signature just has some more operations. The parser signature depends on the string signature, but otherwise it just also defines some operations itself. And then when I actually implement my function, I just import the signatures, and that there wasn't very much code I needed to rewrite, and more stuff. So you can actually I submitted a pull request. They shouldn't take it because it would cause the package to not work on anything that wasn't GHC 8.2, but it's there if you want. So let me just wrap up. So Backpack is a new language for writing mixin packages. These are packages where you don't have to specify all implementations up front. You can leave some for later, so your users can specify exactly how they want to be implemented. It's shipping with GHC 8.2. If you use Herbert's PPA, you can actually get versions of GHC and Cabal which know how to do the lingo, and you can try it out. I have a blog post with some code that you can actually run. And the big idea of Backpack is modularity matters most for big systems. How do we build big systems? We write packages. So our module systems should operate at the package level. And when you do that, you get something very cool, and that's Backpack. Thank you. Do we have time for questions, or should I move it along?
Questions are
Okay. Any questions? Yes.
So, in other talks of Backpack, you've talked about how type classes don't solve the problem Backpack solves.
Yeah.
So I was wondering, what if I'm a very strange individual and I want to use Backpack to solve some of the problems type classes supposedly solve? So I was thinking, what if I want to write, say, just a simple Backpack package that takes two types, A and B, and provides a conversion function between them? And how that, what weird cases that would run into and how I might be able to use it.
So the big thing that type classes give you, and the reason you want to prefer type classes, is that they can be automatically filled in for you based on the types. Mm-hmm. And so Backpack won't do that for you. Mm-hmm. You have to explicitly say, so the idea behind mix and linking is you just bring in something which has the correct name, and that sort of fills in the requirement. So there's less typing certainly, but it's not as implicit as I just need something that works on ints. Let me get that. So a conversion function, like you described, is actually not a bad use case for Backpack, because sometimes you want to write this conversion function where you don't know what A is, you don't know what B is, and when you do this with type classes, you end up with sort of these ambiguity problems where it doesn't know which dictionary to pick because it only knows, oh well, I want A, but what is B supposed to be? So how would this work out in Backpack? Well, you write a signature for A, you write a signature for B. I guess these would be very simple ones. They just say there's some type A, there's some type B, and then you write a signature which specifies the functions that convert between them. And so the only downside is you always explicitly say what A and B are. But maybe that's what you wanted, and so maybe the overhead is not as big. There was another question back there.
Yeah. So in your examples, you have this autoparsec indef, and then you can kind of instantiate it to an autoparsec that uses text or byte string.
Yeah.
Is that if everyone is on Backpack, can we just use the one autoparsec indef package, or do we kind of have to publish these different? Like
So if everyone's on Backpack, you just use the autoparsec indef, and then at the very end of the chain, the user is like, oh yeah, I wanted text. And so they instantiate it with text, and now they get some runnable code.
Okay.
So that's the dream. That's where we want to be eventually.
Okay, cool.
But in the meantime, people can publish these sort of these instantiate libraries along the way to make sure that old code, which isn't parametric, still works. And
Right.
I think that's a strength of the Backpack design. Other questions? Okay, well, I will cede the floor to our second speaker in that case.